SwayamPrabha. Digital India. Educated India.
Hello and welcome to the 10th lecture of the machining science course. In our last session we were discussing the sliding friction, and we said that when the two solid bodies meet each other, since there are asperities and solid surfaces never come with a very smooth surface, absolutely smooth surface if you look under the microscope. So, normally they meet on the asperities, and therefore, the real area of contact, which is the area of those asperities on which they are resting, differs from the apparent area. Apparent area is the same as the geometrical area of mating. Now, if we see here in the slide, we have two surfaces which are meeting on the asperities, as I said. So, initially when the normal force is not very high, these asperities will be deformed elastically because of the normal force acting, and then as the normal force is increasing, then these asperities will be deformed plastically. All right. Now, here if you see, whatever I said, that since the solid surfaces have asperities, the real area of contact, and you can see the real area is shown here. It is the area of the asperities on which the two surfaces are meeting. This is the this differs from the apparent area, and apparent area is the geometrical mating area that depends on the size of the parts. Okay. In case when the load increases, the asperity deformation becomes fully plastic. This is the normal load that we are talking about, and the real area of contact is then a direct function of the applied load. Okay. So, when the force is increasing, then we can write that the real area of contact is equal to n by sigma y. Okay. Sigma y is the yield stress of the softer material. Now, this is, you understand that the area is equal to force by stress. So, here it is a normal stress. Now, during the sliding, when they start sliding on each other, these welded asperities will be broken, all right, and the mechanism is described by the adhesion theory of friction, which gives rise to a formula of the friction force, which is determined by the product of tau shear stress and the real area of contact between the surfaces. So, here we have the normal force is equal to A r into sigma y, and here the friction force is equal to tau and the A r. So, in both cases we are considering the real area of contact. Okay. Now, mu, which is a coefficient of friction, this is equal to, we have seen earlier, the friction force upon normal force, and the friction force is given as the tau into A r, and the normal force from here we can get like normal force is equal to A r and the sigma y, which as I said is the yield stress of the softer material. So, therefore, the ratio of F and N will be tau A into A r divided by sigma y into A r, which essentially means that A r getting cancelled equal to tau upon sigma y. Now, this equation shows that mu is independent of the apparent area of contact. This is very important. the coefficient of friction when the two bodies slide on each other, the coefficient of friction does not depend on the real or the apparent area of contact. Okay. In fact, here you can see that there is no area of contact mentioned here. Now, this ratio of the tau and the sigma y, this reasonably remains constant for a wide range of material. Okay. And therefore, for a given metal, this mu remains constant. That means, the F is proportional to n, or F by n is constant, F by n which is mu. Now, this is what happens in the case of the natural or the normal sliding friction, when the two bodies are moving on each other and the normal pressure is not very high, so that the apparent area of contact and the real area of contact become the same. It does not become the same, because asperities, although they get plastically deformed, but they do not get plastically deformed to that extent when the real area of contact becomes equal to the apparent area of contact or geometrical area of contact. Okay. Now, what happens in metal cutting? In metal cutting, the coefficient of friction can vary considerably. Here we have seen that in sliding friction, F by n, which is mu, this remains constant, because F by n is actually the ratio of the shear stress and the normal stress, which for a given metal remains constant. So, therefore, mu remains constant, and in the case of metal cutting, the coefficient of friction can vary considerably, and this variance, why it varies? Because the normal pressure applied by the tool onto the workpiece is very high. Particularly, it is maximum when the tool tip is in contact with the workpiece, and along the chip tool contact length, okay, it gets decreased. So, therefore, this variance of mu results from the very high normal pressure that exists at the chip tool interface. Chip tool interface, when the chip is moving along the rake face of the tool, causing the real area of contact to become equal to the apparent or the geometrical area of contact over a portion of the chip tool interface. What we mean to say is that, suppose if you see that this is the chip, all right. Let us say this is the workpiece and here is the tool, all right. So, in this contact length, chip tool contact length, we said that the coefficient of friction varies considerably. This is, let us say, h, some distance, chip tool contact length. Now, here this portion, or at this point, the pressure is maximum. Therefore, at this point what happens is that the real area of contact becomes almost equal to the apparent area of contact or geometrical area of contact, and as it goes towards the point where the chip loses contact with the tool, then it decreases, all right. So, that is what we are saying, that over a portion of the chip tool interface, at that portion where the normal pressure remains sufficiently high, so that the real area of contact becomes equal to the apparent area of contact, because the pressure is so high that those asperities get plastically deformed and it becomes like this, as it is shown in this picture. So, you can see that here these asperities have been maximally deformed and the normal the real area of contact is almost equal to the apparent area of contact. So, here the F, this is actually F, you can consider, here it is written FF. So, this F friction force then equal to AA into tau and the F. Tau F is the shear stress, AA is the area of apparent area of contact. So, since here the real area of contact is equal to apparent area of contact, here we are saying that the AA into tau F. So, now if you see the curve, if we draw the curve between normal force versus friction force F, then we will see that this curve goes like this. Okay. This can be explained in the following way, that as the normal force is increasing, as it is increasing, then to some extent up to certain point the real area of contact is not equal to the apparent area of contact. So, there the rules of sliding friction apply, and here the mu remains sufficiently constant, because the real area of contact is still less than the apparent area of contact. Now, as the normal force increases after a certain point, okay, then the normal force becomes so high that real area of contact is becoming equal to apparent area of contact, like it is shown in this figure, and the normal rules of the sliding friction do not apply there. Then the mu does not remain constant, or F is not proportional to, it is not proportional to n anymore, as it is in here. Here up to this point the F is proportional to n. Therefore, the mu remains constant, and beyond this point, when the force is the normal force is very high, okay, normal pressure is very high. So, therefore, the mu does not remain constant here, and the curve goes like that. So, there the F does not depend on the n, or they are not proportional to each other. F is not proportional to n. F is now independent of n, and the ordinary law of friction no longer apply, as I said. Under these conditions, the shearing action is no longer confined to those asperities, okay, and it happens inside the softer material. See, so far what we have seen in sliding friction, we said that the normal force is not sufficiently high. So, the asperities get, although plastically deformed, but when the shearing happens, those asperities or welded asperities, they get sheared off. Here what happens is that AR and the AA, that is the real area of contact and the apparent area of contact, they are same, and then when the sliding occurs, the shearing happens not along the asperities, but it will be from the softer material. So, within the body of the softer metal, the shearing action will take place now. Now, this has been explained in a scientific way through a model, and that model has been explained by Professor Zorev. He is a Russian scientist, and this model is, it says that if you have the metal cutting process represented in this way, that this is the chip flowing over the rake face of the tool, then this is the contact length, chip tool contact length, here it is shown as the LF. Okay. Now, within this chip tool contact length, let us say from the tip where the normal force is maximum up to a certain point, the normal force remains high, and here the shear stress is maximum, okay, and the shear stress is given as tau st. Tau st, because this is the zone which is called the sticking zone. Here the tau remains constant, tau is the shear stress, it becomes maximum and it becomes constant, because the normal force is very high in this region. As it goes beyond this point towards the point where the chip loses contact with the tool, then the normal force decreases, and therefore, the F remains proportional to n, like in the case of the normal or sliding friction, and then the mu is constant. So, this zone from here up to the point where the chip loses contact with the tool is called the sliding zone, and from the tool point, from the point of the tool, tip of the tool, here it is called the sticking zone. So, Professor Zorev's model says that the normal stress distribution on the tool face, here it is the normal stress distribution, and the normal stress distribution is maximum at the tool tip, as you can see. Okay. And as it goes towards the point where the chip loses contact with the tool, it becomes less and less. So, here it is maximum. So, this is given as sigma f maximum, and this curve can be described as the sigma f is equal to some constant q x to the power y. Y is a constant and x is the value starting from the point where the chip loses contact with the tool. Here the x is equal to 0, and as it moves toward the tip of the tool, the length increases along the LF, and at this point the x value is LF. So, x value varies from 0 at this point to maximum, which is LF. Okay. Now, the length of the sliding zone, this will be LF minus LST if the LST is considered to be the length of the sticking zone, where the tau remains constant and the tau remains maximum. So, overall the distribution of the normal stress and the distribution of the shear stress will be as it is shown in the diagram. Now, x is the distance, as I said, along the tool face, from the point where chip loses contact with the tool, and q, this one, and y, these are constants. Now, sigma f, that is the normal stress, that will be maximum, as we said, that when the x, this value is equal to LF. Okay. Therefore, the sigma f maximum can be determined as, if we put the value of x as the LF. So, it will be q LF to the power y. From here we can find out the constant q, which will be sigma f maximum, and we will put the LF to the power y to the left side, which will be LF to the power minus y. From here we can find out that the sigma f, okay, here we are putting the value of the q, which is the constant value here, and if we put the value here, so it will be sigma f max x divided by LF to the power y. In this we are putting the simply value of the x, and this x is here, okay, here, and the q value we are putting it here. So, totally ultimately what we are getting is the sigma f is equal to sigma f maximum LF to the power minus y, and x is remaining here. Now, in the sliding region, what happens? In this region, sliding region, from x equal to 0 to x equal to LF minus LST. Okay. So, x equal to 0 here and x equal to LF minus LST, as I said, LF minus LST. In here the mu is constant because it is a sliding zone, and here the normal force is not very high, and therefore, the real area of contact is not equal to the apparent area of contact, and the real area of contact remains less than the apparent area of contact. So, therefore, mu remains constant, and the distribution of shear stress in this region, this distribution of the shear stress in this here tau, this can be written as the normal stress into mu. Okay. Now, the mu here and the sigma f, we are putting this value through the sigma f maximum, and it becomes this. Okay. Now, in the other length, that is the x equal to LF minus LST, I have repeated this figure here. So, from x is equal to, from this point, that is the LF minus LST, up to LF, in this region what happens? The shear stress becomes maximum, as we said. So, this tau shear stress is equal to tau ST, let us say this is the maximum shear stress here, all right. Now, if we integrate, sigma f is equal to sigma f maximum x by LF to the power y, which we have seen here, all right, which is this equation. So, if we integrate, then we can get the normal force, because this is the area, and the normal force will be width of cut A w, and we are integrating from 0 to LF. Okay, 0 to 0 is x here and x equal to LF here. So, we are getting the area under this curve, and what we are getting is the normal force equal to A w 0 to LF integrated f sigma f, and the sigma f is sigma f maximum x by LF to the power y with respect to dx. So, this is giving, if we integrate this from 0 to LF, it will be sigma f max A w is constant, LF we are getting, and divided by 1 plus y. All right. Now, the friction force, we got the normal force here. Similarly, we can get the friction force, and it can be obtained if we take the summation of this, okay, and this. That means, here it is constant tau s t. So, tau s t L s t into A w is the width of cut, plus we are integrating this, and to get this area under this curve, this will be from 0 to LF minus LST, all right, this from here to here, and we are integrating this curve. So, this will be, this curve can be described as mu into this, right, because mu into sigma y f will be the tau f. Okay. So, we are integrating this portion, and we are getting this constant value. So, that the area under this curve can be obtained, which is actually which will give us the friction force F. Now, this we can find out by integrating this mu and the sigma f, it will be this value, and here it is constant. So, F is equal to this. Now, at the point x is equal to LF minus LST, again this figure is repeated here for convenience. So, x is equal to LF minus LST is here. At this point, the normal stress is given by tau s t by mu, because earlier we have seen that normal stress into mu is equal to shear stress. So, therefore, the normal stress can be given as tau s t divided by mu at this point, but here from this side we can find out that from equation 1, here is the equation 1, sigma f is equal to sigma f max x by LF to the power y. So, in here if we put the value of x is equal to LF minus LST, then the sigma f max can be found out as this LF minus LST by LF to the power y. We are simply putting the value of x as LF minus LST. So, sigma f will be this value. Therefore, mu into this sigma f at that point will be equal to tau s t, okay, because the mu into normal stress is the shear stress. Now, the f that we had earlier, this equation we have derived by integrating these two sides, okay. And if we put this value here, then substituting this equation 3 in this equation 2, if you can see this, that here it is remaining the same, all right. And then instead of this portion, we are putting the value of tau s t. So, this value will be put in here, and remaining will be A w LF minus LST to the power y gone. So, it will be 1 of this, that is LF minus LST divided by LF to the power y is here. So, it will be only 1 plus y. Okay. So, this is clear that this is how we can simplify the value that we have derived by integrating the curve, okay, to get the shear force F. Now, we have the normal force that we have found out, and normal force we found out from here if you see I have just repeated this, and we have the f that we have derived and simplified here. Then we can find out the mu or the tan of the friction angle. Tan of friction angle is equal to f by n, and if we divide this expression f, which is in equation 2 and simplified here. So, this value of f we are putting in here, and that we are dividing by the value of n which we have obtained from here. So, this will give you the tau st divided by sigma f max and 1 plus y LST by LF, if we divide this by this. So, in here of course, so that you are not confused. So, this is actually f, okay. This is f, and this is the same f, which is obtained by substituting this equation, okay, into the equation 2 in here. So, then lambda is friction angle, and the tan of lambda is f by n. This is the shear force, this one, and the n is the normal force. And n, once again I will remind you that n you can get by integrating the normal stress curve and the area under that we are getting, and we are getting the stress, the shear stress if we are integrating the shear stress curve. So, under that we are getting the area. So, that would be the shear force. So, shear force divided by normal force will give you this equation, which is equation 4. Okay. Now, the mean normal stress on the tool face is given by this normal force if you are distributing along the chip tool contact length and multiplying by the AW, so that we can get the area. Okay. So, length into the width. Now, what we are saying is that we have the normal stress here, all right, and we are getting the average value of the normal stress. Average value of the normal stress, then we will be the norm, we will get it by dividing the normal force, and this is distributed along the chip tool contact length. So, that area we can find out by AW into LF. So, if you divide n by AW and the LF, you will be getting the sigma f max divided by 1 plus y. Now, sigma f max, therefore, we can find out by multiplying sigma f average into 1 plus y. Okay. This is the expression, therefore, we are getting for the sigma f maximum finally. Now, substituting sigma f max in the equation 4, in this equation we have the sigma f max, and this we are substituting, then we will be getting the value of the lambda through the arc tan, and this will be the arc tan of this value. Okay. Now, in experimental works, it has been found that the term tau st, this and this remain sufficiently constant. Okay. For a given material over a wide range of unlubricated cutting condition, and therefore, this expression becomes the tau is equal to arc tan, which is constant, let us say this is some constant k divided by lambda f and the average. So, this is how we can actually express the friction angle or the coefficient of friction. This is the same thing, because we said that the f by n is this and this is the tan of the lambda. Okay. So, lambda is the arc tan of f by n, finally we got it in this way. All right. So, this has a significance, that is the result of Professor Zorev's model on the friction in the metal cutting, and the consequence is that it means how the mean angle of friction depend on the normal stress, all right, and how it varies when our normal rake angle changes, which is the working rake angle, as we have seen earlier. For example, we said that normal rake, orthogonal rake and the side rake angle, they influence the cutting force and the power, and how we can conclude from this equation that how they vary. I will discuss it in the next class. Thank you for your attention.